So today we're talking about multivariate spatial models. So again, weeks 1 and 2 we get up to speed on T and D and generalized linear mixed models. Week 3 we did time series. Then week 4 we were doing a little bit about multivariate time series models, so multivariate Kalman filter. And that's sort of the only time we've talked about sort of multivariate models. And then we transitioned into kind of 1D space, 2D space, space-time models by week 7, and then this week we're looping back to multivariate spatial models. So in ecology, these have gotten pretty popular in a very small set of people as what are called joint models. So if you look at kind of biogeography in general, I mean, like going back all the way to like Humboldt, like ecologists go out and start inventorying different continents in sort of a colonialist way, and trying to figure out what's in the New World, and we started seeing kind of patterns really quickly in some areas being species rich and some being like species depauperate. And I actually had a reviewer tell me never use species rich because it's too normative, so I should say specios. I think that's what we decided.
What?
But ecologists love arguing about normative terminology, let's just say. So we've got specios and species depauperate areas. And so like in this paper of North American birds, the Breeding Birds Survey, which is sort of the biggest like spatial data set of birds in most continents, we've got these samples where people go out at different transects, and each transect they report the number of different birds they observe. These are citizen scientists essentially, and so there's some correction for skill of the citizen reporting it. But we kind of get these broad patterns where like, in the Northeast, in Appalachia, you get your like, MacArthur's like walk warblers, that all like occupy different parts of a tree, and there's a lot of songbirds in the Northeast, and then I guess for some reason in the Rocky Mountains you get fewer birds in the raw data or in fit a spatial model in terms of woodlands or forests. And this is interesting because, well, it says something about some kind of general like landscape impact on, diversity and ecosystem function. But on another level, you can think about it and say that the distribution, if you look at the distribution of each individual species that's included, that there's a bunch of species that have higher encounter probabilities in the northeastern U.S. and lower in the southwest, for instance. And that basically means that the distribution of multiple species in the community are correlated. So if you want to predict distribution for some unobserved bird, you might be able to gain some information from the birds that you have sampled to say that, it's probably more likely up in the northeast and less likely in the southwest. And so that correlation among species is sort of what the joint models are trying to pick up on. I don't know. I mean, really, I should probably flip this around. I think people here all have done something with distribution at some point, distribution models. Anybody willing to talk about why they care about them?
We wanted to figure out where kind of people were targeting sharks and find out a little bit about their spatial ecology.
Totally.
Like what sort of geographic features they like and temperature ranges and stuff like that.
Yeah. Wait, what area was that?
Peru.
In Peru. Yeah, cool. And were you trying to figure out if like sharks were following environmental conditions, or whether there was like a productivity, like an impact of local conditions on productivity, or
local conditions of productivity? And then I did a follow-up trying to figure out if they followed conditions, but never published it.
Okay. Yeah. like for mobile species, it's often hard to sort out that, like, are they moving to good conditions, or do good conditions actually help them grow faster?
Yeah, I just broke it up in like El Nino, La Nina, and common years, and you can see them like moving up and down the coast.
Totally, cool. Yeah, right, and like for fish species, a lot of times that's like, there's a whole interest in distribution for like bycatch modeling. Yeah, so like we have these sort of real-time maps of distribution for sea turtles and whales and sharks, and then do like real-time spatial closures or whatever. How about you, Nat? Like a public health example?
Sort of thinking, I mean, you can sort of model the incidence of like children dying as sort of a species, and I think it's pretty similar in terms of finding covariates. There's different levels of observation across different areas. So that's sort of that's what I'm working on right now. So it's sort of the thing that I'm thinking about most. But also like, diseases like epidemic, Zika and stuff like that can be modeled as a species that is found in different proportions in different places.
Yeah, there's sort of this like putting in covariates, like oftentimes people, like an economist might call that, I want to call it a structural model, like statisticians also call it a structural model, where if you specify a structural model correctly, you can, estimate the causal impact of a covariate on a response. And so, like in public health, I imagine it would be like translated into like, oh, if we could improve income by X, it would result in a net impact of 5% lower child mortality or something.
Yeah.
And then the Zika thing, hits on the kind of broad point of like forecasting invasions, forecasting future distribution shifts under, for invasions. Abby, do you have any thoughts you want to chip in?
I collected data that was going into a model for British butterflies, like modeling range shifts.
Cool.
With kind of climate change.
Like with, who were you working with on that?
It was Oxford Uni have an environmental group, and I can't remember the lead kind of researcher. I was literally just looking through like data and figuring out. Yeah.
Yeah, I've seen I think a guy named Morgan Bryan give talks, and he's somewhere doing butterfly models at the continents.
It's all about butterflies.
Yeah, that's funny. Totally. Yeah, so there's some, I've seen him talk about is there different trends for urban versus rural butterflies, and some thought that urban butterflies are going down, I think. So people care about trends. Yeah, I mean, and then I think that the thing that we kind of didn't maybe hit on that I talk a lot about around NOAA is that I think distribution maps are just sort of more intuitive, than some of the other ways we present results. So, people, I don't know, I saw that, I saw some news that Google Maps was going to start using, neural network, AI stuff to predict, creepy shit about us. And, but, everybody's used to seeing Google Maps. It's the most familiar, really complicated augmented reality tool that we use daily, so you can have a very sophisticated kind of map, and have it seem really intuitive to people, even though it's not, and I think that those sort of distribution as a communication tool is sort of one of the things I'm really excited about. And then, spatial ordination. Sometimes people ask me what ordination means. Does anybody want to try to define ordination?
I mean, it's sort of like trying to find which ones are most similar to other ones and sort of group them together and then
totally
maximize the similarity within a group and the difference between groups.
Totally. Yeah. So I'm trying to think, back in my sort of reading about, historical ecology, there was sort of like ecology, I think, grew out of people thinking that or they're famous community ecosystem ecologists. They're oh, there's a certain biome and there's this other certain biome and all the species in that biome, kind of go together, kind of work synergistically, you know, and in that kind of biome world, you know, there'd be like a single factor that represents like at this location, it's like mainly biome X or mainly biome Y, and you could ordinate, you could map the distribution of each species down onto basically a single kind of variable representing what biome you're in. And then, you know, like later, like Whitaker in the 50s gets into sort of like these claims that like each species has a totally different distribution, and so there's not, you know, there's not like species aren't just constituents of kind of communities that are homogeneous, but instead every species has its own unique distribution. And so there, you know, there's a lot of classic questions of ecology that are kind of questions of ordination. You know, how much can we map the distribution of species in a community down to kind of a small number of variables? I also think of it in terms of rank reduction, and we'll talk about rank reduction more in a bit, but does anybody remember how we defined rank, like an eigen decomposition of a covariance matrix? I know you remember, John.
If it's the eigen decomposition, then it's the number of non-zero eigenvalues.
Yeah.
So it's sort of the number of linearly independent components.
Exactly, yeah. So if you have 100 species, you could have 100 by 100 covariance matrix between those species. And in this sort of, and I wish I could come up with a name for kind of who I associate this with, but I think oh man, I don't want to guess. But, you know, in this sort of like really early 20th century sort of terrestrially, you know, plant ecology world, you know, if you had 100 plant species, you might only have, the covariance might have a rank of 2, you know, where there's sort of one eigenvalue that's associated with like wetland to your like forest to plains, and another one that's associated with elevation. And in this world, you only need those 2 variables to predict everything about a community. Whitaker, by contrast, is in a world where, you know, if you've got 100 species, it's rank 100, where every species has some kind of unique contribution. You know, there's no way to map all the species down onto a very small subset. And we'll kind of formalize that a little bit more as the class goes. Yeah, let's see. I should probably change that. Nah, this is fine. Maybe I'll change this a little bit. I'll say that the covariance is operating in log space, because that's the way we usually model it later. So we might have you know, Poisson distribution for counts, like we've used, you know, since week 2 or something. For, you know, where count C is a you know, a whole number, you know, 0, 1, 2, 3, 4, etc. And then it's you know, indexed by P, and I'm going to use subscript P for species, and I'm using it as a subscript because it's integer valued, whereas S could be continuous valued over space. So CPS is the count of species P at location S, and it's Poisson distributed with intensity lambda for species P at location S. And the covariance between the log of lambda, I mean, we take the lambda has to be a positive real number, and so the log goes from negative infinity to infinity, and the covariance, across space for lambda of species P1 and lambda of species P2 has some covariance V, where the full matrix of covariance, capital V, is the covariance among species. And so really the question is, how do we efficiently model that covariance matrix? So again, like this guy Latimer published an Ecology Letters paper in like 2007 where he did this with a 5-species model. And then, you know, James Clark did a 2013 paper where he kind of advocated doing this. And then that's where sort of like, well, in my reading of it, like Obaskainen and I and some others all came up with this sort of factor model that you can apply to hundreds of species. So we can scale this spatial model up to hundreds or maybe thousands of species. I don't think anybody's really mapped out the limits of it. So in terms of how we've thought about this before, let's see, I'm sorry, this is kind of silly. I'm going to go back to, yeah. Here. Yeah, that's fine. Okay, so this is the same count data model. We'll say that the log of lambda has this linear predictor where beta p is an intercept for every species. So in this case, every species has a, you know, some species have a high beta p representing that they're kind of high numbers, you know, high abundance across space on average, and other ones have a low beta sub p, meaning they have low abundance across space. So that kind of identifies which species are numerically dominant or rare. And then there's this omega ps that represents spatial variation. We've been using omega for spatial variation for most of the class. And omega ps is a matrix. You know, they'll have, the way I usually notate this is S is the rows and P is the columns. So if you've got 100 sites and 10 species, you've got a 100 by 10 matrix. And if you take the vec operator of that omega, so take the matrix and transform it into a 1,000 linked vector in this example, then that 1,000 linked vector is mean 0, so that it's not confounded with the beta p, and it has a covariance equal to the Kronecker product of the covariance among species and the correlation among locations. So this is the separable specification where we can use this Kronecker product. The V species has, dimension. In this example I'm using, V species has a 10 by 10 covariance matrix. And the R spatial is going to be 100 by 100 spatial correlation matrix. And so the Kronecker product is 1,000 by 1,000 covariance matrix, which is the right size given that we're, in this example, vec of omega has a length 1,000. And we know how to do a sparse, a sparse version of the inverse correlation matrix, so that R species we can specify, we can estimate efficiently, and we've been doing that since week 6 or 5, depending on if we are doing 1 or 2 dimensional space. But the new part is that V species, where I think in week 4 we were doing these time series models that were dense. So we had a Kalman filter, a time series, a multivariate Kalman filter that had 5 time series, and we just had a dense 5 by 5 covariance matrix. And at this point, we want to figure out how to do that covariance matrix in a way that's more computationally efficient. So the trick that I started with was this. It's the same trick that factor analysis uses. And so I've been calling this spatial factor analysis. And that trick is based on the Cholesky decomposition. So the Cholesky decomposition of the covariance matrix gives you a lower triangle matrix where all of the diagonal and everything below the diagonal is non-zero, and everything above the diagonal is 0. That's the definition of Cholesky, and we call it L for lower because it's a lower triangle matrix. And you can take that Cholesky and then trim off some of the columns, and so you end up with this rectangular matrix that has fewer parameters, and you can reform the covariance matrix from this L times its transpose. So you can take the trimmed Cholesky and treat it like your original Cholesky, multiply L by its transpose, and then you get back, if you have a 10, like for example, you have 10 species and 2 factors, and you're in this world where you think that all dynamics of species can be explained by a small number of factors. Then you might have a 10 by 2 matrix for your trim Cholesky. That times its transpose gives you a 10 by 10 matrix, which is the same dimensionality that you need. Except the rank of the covariance matrix is now equal to the number of columns of that trim Cholesky. So I'm kind of just outlining this instead of trying to elicit it by question and answer. We've got kind of a smaller class. But maybe we should ask some questions. This is kind of the meat, the kind of mathy meat of the technique, and then we can kind of go through code to try to build up some intuition about it.
I mean, how do you not lose information when you trim out some of the columns?
You definitely do lose. So you're projecting those 100 species onto a lower dimensional subspace, basically. So the trick, though, is that in a mixed effects model, it's going to try to explain as much variance with the random effects as it can. And so if you have the 10 species and you only give it 2 factors to use, it'll find the 2 factors that explain as much of the variance as possible. And so it'll basically generate the 2 factors that are most important in explaining the overall distribution. So you kind of lose the minimal amount of information, and by doing so, you can do this rank reduction where you capture what's the 2 most, or in this case, in this column, the 3 most important kind of underlying factors to explain the distribution of these 7 species.
Oh, you got a question?
Online. So yeah, so we don't decide which ones to trim off. The model will, we specify how many columns we want, and then the model is going to estimate the parameters of that. And again, as I was saying, a mixed effects model will try to have as much of the variance explained by the random effects as it can, because that's the solution that maximizes the marginal log likelihood. And so in this case, if you give it two columns, it'll rotate those columns such that they explain as much variance as they can. And, while also having the smallest variance estimates. So one consequence of that is that spatial factor analysis will kind of automatically generate columns that are orthogonal to one another, in expectation at least. And so there's nothing that we're doing to specify them, these columns, as orthogonal. But the model, just during parameter estimation, will automatically kind of make them orthogonal. So there's a lot of different instruments. So Caitlin, or Elizabeth Offsite asks, what's the interpretation of the columns and factors? So I call the factors the omega. So if you've got 2 factors, that means that P could be either 1 or sorry. I call that here. We haven't gotten all the way to the full notation yet, but so I'll go one more slide and then I'll come back to your question, Elizabeth. So writing out the model, you can write it like this, where it estimates some latent mass, which I call factors. It separates process and measurement error. So the measurement error is in that Poisson distribution, or you could have a negative binomial, or you could scale this up to a delta model or whatever. And it derives the covariance between species from the loadings matrix that you estimate. So that's the kind of co-occurrence among species or among diseases or whatever is predicted from that loadings matrix.
Which one was the loadings matrix?
Well, okay, I'm sorry. Yeah, it's kind of a pun where L is the lower matrix of the is a lower triangle triangle matrix from the Cholesky decomposition. But in a factor model, factor analysis was developed by it's like a famous kind of psychologist and statistician whose name's escaping me right now. Spearman, maybe, or somebody could Wikipedia. Factor analysis uses essentially the same notation where they use L and they call it a loadings matrix. And so you can kind of remember that L stands both for the lower triangle Cholesky decomposition, but it also stands for the term loadings matrix.
In this case, is the loadings matrix also the lower Cholesky where we took off the few columns?
Yeah, exactly. So the loadings matrix is that trimmed Cholesky. Okay. And you can have as many factors as you have responses or species, in which case you'd have just the full Cholesky. You wouldn't have trimmed off anything. But the equation that I'm going to use is this, where we've got the standard count data model where lambda is this matrix of S and P, and it's predicted from this intercept for every species, and then the product of a loadings matrix times a factor omega. So I'm calling omega the factor and L the loadings matrix. And you sum across all of the different factors when you're calculating the kind of net effect of the factor model. So this you basically take the product of a row of the loadings matrix times the factors, all of the factors at that location, and put that in your linear predictor. And that's what this summation, the sum n from f equals 1 to nf, where nf is the number of factors. You're summing across the loadings matrices times the factors. So to get to your question, Elizabeth, the interpretation of the factors is that they're sort of these latent variables that explain covariance between species. And the loadings matrix L is the effect, it's the action of a given factor on the distribution of a given species. So L is sort of the link or the loadings of every factor on every species. And the omegas are the maps, these spatial factors that represent latent variables. So we'll keep going through examples, but is that helpful to start, Elizabeth? Or do you want to ask a follow-up? Exactly. So there's no covariates in this model so far. Elizabeth asked if the factors have anything to do with covariates. And so far there's a fixed effect intercept beta, and then omega is all random effects. And so this model has nothing that I'd call a covariate. You can put in covariates, and then it will kind of control for those covariates, and then the factors will represent the kind of correlated residuals after accounting for the effect of covariance. So the first example I did in 2015 was looking at the distribution of these rockfishes off the west coast. So the Oregon, Washington, California, and these density maps where orange is high density, blue is low density, and this is, I think, the predictions from this factor model for a given year, probably like 2003, and I forget what 10 species these are. It doesn't really matter for our purposes. But there are some species that have this sort of coast-wide distribution on the slope, so the top left is kind of coast-wide. The second row, second from the left, also is kind of relatively coast-wide. The third one from the left on the first row, maybe kind of more coast-wide. And so you kind of guess that those ones maybe share a factor. Maybe there's one factor that represents sort of coast-wide species, and then maybe there's another factor that represents that kind of discriminates between northern versus southern species. And if you look at the factors that are estimated, they end up looking like this. So, in this model, I guess, there was one factor, the left factor, kind of generally accounts for species that have high density, kind of, middle Oregon and south. And then there's another factor that represents kind of high density, kind of northern California, northern and north of there. Then this next factor is sort of the inverse, like where blue is high density, just kind of coast-wide and the kind of slope. So this third factor might be the coast-wide kind of one. And then this fourth factor accounts for, I don't know, it kind of looks like the second factor, except maybe a little bit farther off the slope. So these factors by themselves are kind of hard to sort out by eye for reasons that we can kind of come back to later. Back in 2015, I didn't know how to visualize these as well as I could yet.
Is there any like biological interpretation of these factors, or?
Yeah, so why don't I come back to that? Let's see if I've got a bird example that I use that is more easy to interpret biologically, and I don't have it. But so I'll pull that up in a minute. Let's come back. One thing I did with this paper was, so again, this covariance you can get from the trim Cholesky times its transpose. And if you look at the analytic correlation among species using these factor models, you can see sort of this strong patterning where species 6 in this case is negative, where blue is negative, white is 0, and red is positive. And so species 6 in this case is pretty negatively correlated with most of the other species, whereas the remainder of the rockfishes are pretty positively covariant or correlated. Instead, if you just fit a distribution model to every species independently, predict density, and then take the sample correlation among those predictions of density, you get a much more confusing picture. I mean, it kind of looks like the other correlation, but it's just kind of white, it's kind of like a whitewashed. I mean, it's kind of like a noisy representation of this, is the claim. So you can get more precise estimates of correlation from these joint models. And that's something that kind of has been replicated in the literature. And the problem, of course, wait, no, I'm sorry, okay. So this is the predictions from the multi-species model. This is the multi-species model that I can then use to predict density for every species. And the sample correlation looks kind of like the predicted correlation from the model, except noisier, because that makes sense, because this is the predictions of density, so there's kind of additional variance that's built into it. If you fit a lot of single species models individually, the analytic correlation that you're assuming is that every species is independent, and an independent model for every species is essentially an implicit identity matrix with a correlation. And if you predict density from those single species models, you get something that just looks like gibberish. So the predictions of density from the stacked single species models has no pattern. And that is a red flag in this case, because we know a lot of the rockfishes have, similar, similar, I mean, they differ in a variety of ways, but these are all bottom-associated rockfishes that are all kind of shelf and slope species. And so you wouldn't expect them to just vary as kind of a scatter shot. So, the stacking, like James Clark in his 2013 paper made this point, that if you fit a bunch of single species distribution models and then try to work out kind of community patterns from that, you get a couple problems. One of them is it's really noisy. Another one is that your kind of implicit assumptions don't match the model predictions at all. And so you get kind of the wrong inference about, kind of community level inference. I think that this probably also happens at IHME if you do a global burden of disease map on every mortality factor individually. You are probably missing the big picture story of like a lot of them are covariating, and so you end up with a much noisier measure of total mortality than I would imagine is really occurring, where you've got a couple factors like income and temperature and whatever it would be that would drive mortality across a bunch of different agents. Right, I think, yeah. So there's sort of this mismatch between the assumptions and the predictions when you stack single species distribution models. You can also get better predictions. So if you do a bunch of single species models, fit into year 2003 and then predict distribution the next year and take the kind of rank correlation between the predictions and the observations and do that for every species and every forward projecting year. If you do the spatial factor analysis, you get a predicted correlation of 0.334. If you do the single species models, you get a correlation of 0.28. So you get this like, 30, 20% improvement, 15 or 20% improvement in predictive performance in this particular measure of it using a multi-species model relative to a single species model. And the predictive accuracy is almost always positive. There's only a few cases where it gets any worse. So it's a pretty like risk-averse way of getting improvements in predictive performance. Yeah. So and then the final. So are people feeling okay about sort of the big picture story? We can talk about biological interpretation more in a second. There's sort of two kind of follow-up pieces, but I want to make sure that people get the kind of groundwork before moving on.
I'm just trying to think about like the limits of like how far you can go with this, because for example, like for our covariates, all of those things, we need them at a spatial resolution, so most of them are estimated from data.
Yeah.
So it's like, could you just chunk in like all of the covariates you eventually want to use and jointly model? Say you've got like whatever distribution of 4 species, but you've also got estimates of land surface temperature. You've also got estimates of like certain like ground cover or something. Like, can you put all of those in a joint distribution and estimate them with this factor analysis?
Yeah, right.
Prediction.
For sure, you can. And I've done that a little bit with like life history traits. So there's sort of this funny dichotomy between people that want to put in covariates on the right-hand side of the equation. And the problem with that is that if you're missing covariates, like land use cover, then you're kind of hosed. Whereas you can put them on the left-hand side of the model and do it as a factor model or a joint model. And if they're missing, we know how to deal with missing observations, and it just automatically calculates the covariance between, our things on the left-hand side, some of which we want to interpret as responses, and some of which we want to interpret as predictors. So John and I are talking about doing that kind of technique generally for kind of like using the sampling intensity as the predictor for densities, but we're putting both of them on the left-hand side of a problem, maybe. And I've been doing that for like history parameters, where people typically want to predict like mortality rates from growth rates of a species. But if you're missing the growth rate, then you can't do that prediction. But you can put both on the left-hand side and just treat them both as responses in a joint model.
And so outside of like computing time or something like that, there's no like obvious downside of doing it that way.
Yeah, the downside is that the way I'm presenting is a covariance matrix, and so it's kind of implicitly assuming it's only a linear relationship between them. So there's ways, in theory, you can do everything either way, but it's sort of easier to do missing data models with this sort of factor joint model, I think. But it's harder to do nonlinear models with this joint model technique.
Okay. Questions on that?
Yeah, so Caitlin was asking about sort of like how to decide what species to include in a joint model, and I think that's sort of how many or what types of species to include in the joint model, and I think that's sort of an open question, research question. I mean, so on the one hand, can anybody remind us of what Stein's paradox was, or
It's like the sharing information provides you better predictive ability.
Yeah, and like specifically that like the James-Stein estimator shares information to get better predictions, but it works even if you've got like 3 baseball players and like proportion of Japanese cars sold in America. So you don't, for this shrinkage to be an improvement, you don't need them to all be identical. It's just if you have a contamination, the shrinkage is less, and so you end up with worse model performance. So on the one hand, you might want to, kind of go for a model with high shrinkage and have kind of, species that you select a priori to have similar distribution. On the other hand, you might just put in every species and kind of let let this model kind of do ordination and figure out what species groupings make sense. That's another meaning of the word ordination, is to kind of use a model to determine which species are similar, which species are different, and that's sort of one outcome of this factor model, is that ordination. Anything more we want to talk about for now? There's sort of these two, okay, so I'll hit two follow-up topics, and then we'll look at code, and then we can come back to it. So one of them is this topic of additive covariance. So so far we're talking about this model, this joint model for species, the separable model for spatial variation and covariance among species. That's formed from this Kronecker product of the covariance among species and the spatial correlation matrix. And in reality, we can have this additive covariance. We talked about how, if you've got two covariance matrices, their sum is also an admissible covariance matrix. And so you could come up with a lot of different hypotheses for the covariance among species and just sum them, and then kind of figure out which of those components explains the most variance, and use that as sort of like a variance partitioning approach to, a better, like a model-based, like Gilman recommends this as a replacement for hypothesis testing. So instead of saying, oh, it's phenomenon A or B or C, you just put in A, B, and C, all of them, and say the proportion of variance explained by A is greater, it's 80%, and so the strength of evidence suggests that A is the most important. That's sort of a more modern way of thinking about the sort of replacing hypothesis testing with sort of strength of evidence estimation. So just as one example, this is the only slide I'm going to have about additive covariance and strength of evidence, variance partitioning. But you can imagine that the covariance among species has this factor model, this loadings, this prim Cholesky times its transpose, plus another hypothesis, plus another hypothesis. And in this case, you could say that one of these sigmas is this taxonomic similarity. So you could say that the covariance matrix has a certain value if two species share the same genus or family, and is 0 otherwise. And so that would be the portion of covariance that's due to kind of taxonomic similarity. And then you could also have a another component that's like life history similarities. You can have a smoother, you could have essentially a spatial model with a squared exponential or an exponential or, Materin or whatever covariance function you want on the dissimilarity between some life history parameter. So in this case, in my work, I've kind of concluded that, asymptotic size of a species is one of the biggest factors, in this rank reduction interpretation of differences among fish species. And so you could say that, okay, well, if two species have the same asymptotic maximum length, which we indicate by L-infinity in fish, then this is 0. So e to the negative 0 is 1, and so they'd be highly covariant. And if they have really different asymptotic maximum size, then they'll have a very low covariance in this life history component. And so if you sum the Cholesky part and the taxonomic part and the life history part, and put that in as the V species, then suddenly you've got this sort of very modern way of asking this kind of classic ecological question of, is taxonomic similarity the most important for driving something, or is life history the most important, or is there some underlying factors that we could extract and look at to explain covariance? So I think this is the power of sort of thinking about additive covariance, in these kind of joint models. And it's something I don't think anybody's done, really, or published. So it's kind of wide open. Any questions about that? Or and then finally, there's this, you can rotate these results using a rotations matrix H. So just like in factor analysis, if you fit a factor analysis model, then people do this like Varimax rotation on the results, typically. But Varimax is just one of kind of an infinite set of possible rotation matrices, and there's different sort of good rotation matrices. Then I'll just talk about Varimax and this sort of PCA rotation. And to start out, you know, I just want to try to convince you that we've been looking at this first equation as sort of spatial factor analysis, but you can just as easily write it out replacing the loadings matrix and the factors omega with some rotation of them, where the loadings matrix L prime is equal to L times this rotation matrix H, and omega is equal to the inverse of the rotation matrix times the original omega. And if you do the algebra, it makes sense that this is equivalent because you've got H times its inverse in the middle of this, and it just drops out. So it's really easy to see that these are equivalent. Can anybody think of, or does anybody know factor analysis enough to kind of explain why this rotation might matter, or what you do with it? I mean, the key is that we kind of, without really talking about it, there's sort of a trick here where L is this lower triangle matrix, and so if you tried to estimate these zeros, if you tried to estimate this full matrix, it would not be identifiable. You could fit this, you could put this into TME, and you could run it to convergence. The inner optimum would work, the minimizer would work, but it would get to the MLE, and it would try to estimate the Hessian. The Hessian would not be positive definite, because it would have, in this case, exactly 3. It would be rank reduced by 3, because there would be 3 axes in that Hessian matrix that were singular, representing that there's some 3 additional parameters that can't be estimated. And so for identifiability, we specify that L is this lower triangle matrix. But we then can rotate it so that we rotate the values of these loadings so that these are non-zero. And then the rotation can be done to kind of basically improve the visualization of your model. So the rotation doesn't actually affect the predictions at all, as we saw. You can rotate it and you get the exact same predictions for all data points, so it's the same, quote, model. But it does affect your interpretation of the loadings, and similarly it affects your visualization of the factors, if you want to put it in a journal or whatever. And so Varimax is one that maximizes the loadings of each factor with a small number of categories. So if you want to interpret, if you want to say factor 1 is associated with, split nose and sharp chin rockfish, and factor 2 is associated with canary and dark blocked rockfish, and not with any other species. And Varimax is one that maximizes the loadings with a few core species for every factor and minimizes all the other loadings. And technically it does that by maximizing the sum of the square of the element of L for every species and factor. The principal component version, which I prefer to do, is just because of the type of work I do. And I actually don't know what a real statistician calls this. I'm sure there's a name. I just never found it. Is to basically mimic what a PCA is doing. So it rotates it so that the first factor explains as much of the variance as it possibly can. The second factor explains as much of the remaining variance conditional on the first, and then so on. And essentially what that's doing is it's maximizing, the sum of the squared element of the first column and then the squared element of the second column, given x is the first, and so on. And so you can think of these rotations as being a way of maximizing some function of L, and they're generally can be done using matrix algebra in some way that's efficient. And they're just a technique to basically rotate the loadings and rotate the factors to ease biological interpretation. So, for instance, if you fit a factor model, like in 2016, I did this dynamic factor analysis, and I fitted all the species in the eastern Bering Sea, and then do the PCA rotation and just look at the first factor, and that factor will represent sort of the maximum amount of the variance in the eastern Bering Sea that can be explained by one length variable. And what pops out is this kind of funny kind of like mix of the cold pool as well as these sort of like residual patterns in pollock and cod. So that there's just like this sort of, without putting any covariance in, you can just kind of pop out sort of what's the dominant pattern in an ecosystem, as they claim. Whereas Varimax is good to interpret sort of like this factor is species A and C, and this one's species B and D. So it depends on your goal. What you want to use. So that's all I'm going to say about rotations. And you can spend a whole class on that, I'm sure. Does any last questions about that, or maybe just switch to looking at the code? I also might call class early because I only paid for parking through 2 minutes from now. So.
Oh, no, right. But maybe the police will be occupied with protests.
Yeah, hopefully. Sure. The one time I hope the protests get really. I'm not gonna say it. So, yeah. So, I'm just loading a simulator function from SimFun, and in this case, I'm going to simulate 10 dynamics for 10 species with 2 factors, and I'm going to estimate 2 factors just to make it kind of an easy problem. So this simulation simulates the location, so 100 locations in X and Y coordinates. And then it has a response that's a count for every one of 10 species. So site 1 has a count, I guess, is pretty high for most of the species. So you can already kind of start seeing that like species 2 and 9 probably share the same loading on one of the factors. And X, SJ, I forget what that's supposed to be. Okay, yeah, so I'm putting in an intercept for every species just as a design matrix. So I then use the inlet just to make this mesh. So to generate this triangulated mesh the same way we always do. As John showed us, we can make a much, we can approximate this random field much better if we fill in vertices in this mesh to, satisfy kind of minimum angle criterion, and border boundary conditions and so on. And, maybe I'll probably get the time. Maybe I'll focus on doing that if I teach it again. We generate the input lists for TMB, and then I'll show the CPP code in a bit. But if we've got 10 species, then we're going to have 10 intercepts. So beta JP is going to have 10 elements that are being estimated. If we've got 2 factors in 10 species, then our loadings matrix is going to be 10. The first column has 10 elements, and the second column has 9 elements. So there's 19 parameters to estimate in the loadings matrix. log kappa is the decorrelation rate for all the factors. That's I'm just assuming that it's the same for all factors to simplify the interpretation of it. And then I've got two factors. Let's see. Mesh. And got 116 vertices in that SPDE approximation, and I've got two factors, so 2 times 116 is 232. And then I can run it, get the report. We can see that it looks like it's converging well because the inner optimum, the U step, is always close to 0, and the MGC is always getting really close. The U step is always close to 1, meaning it's kind of a close to quadratic inner optimum, which is promising for it to converge well. And then while we're looking at that, we can report out the loadings matrix from that was used to simulate the data, and also compare it with the loadings matrix that's estimated by the model. We can compare the covariances, the true or estimated covariance, and we compare the predictions of omega, the factor itself, between the true and estimated. You can see that this runs a lot slower. So when we were doing a univariate spatial model, it would take this long, but it's running slower because basically it's trying to figure out all the covariance between species. And so you start out really far from the optimal covariance. It kind of wiggles those factors around until it gets to the right spot. But yeah, it looks like it's getting close because the MGC is listed occasionally is close to 0. Now it's not showing up, so it's obviously doing the Newton step part to kind of drill it in. Take questions while we're waiting for this.
How did you choose 2 factors?
In this case, I'm just trying to show the code. So one thing you might be asking is like, how do you select, if you've got a real data set with 10 species, how do you know to use 1 factor, 2 factors, 3 factors, or how do you select that? And there's surprisingly little statistical guidance on that in the factor analysis world that I can find. So like when I took a multivariate class, people recommended looking at a scree plot. So a scree plot would be something that looks like a scree plot is the variance for each factor as on the y-axis and the factor number on the x-axis. And if you fit it with a lot of factors, it'll often look like this, where it declines quickly and then it kind of hits a bottom. And so this is called a scree plot because people, it's like a cliff where people fall off. Hit some scree at the bottom of it and die. Like with some red here. Yeah, so that's the scree plot technique. Another one is you could just do AIC to like optimize how many factors to use like we would in a normal model. We haven't really talked about model selection, and maybe somebody asked me on Thursday. There's like some problems with the marginal AIC that people use for this, but it's kind of, for non-statisticians, you could probably get away with it. And then my preferred way of doing it is doing the PCA rotation and looking at the variance explained by each of your factors after rotating it, and just basically cutting any factor that explains less than 5% of the total variance that you want. So that technique usually ends up with fewer factors than AIC. And then finally, like, when people do this dynamic factor analysis, which is kind of the same concept, people just recommend just ad hoc choices. So if you fit a model with 6 factors, you can only interpret the first 3, then just refit it with the 3 you can interpret. So that's still something that people do. even if that's probably not good practices statistically. So this is the result of, so the top one is the true factor model, the true factor loadings matrix, and the bottom one is the estimated loadings matrix. And so, any thoughts on how these compare?
Well, it's multiplied by -1.
Yeah, so one obvious one is that this one it really looks pretty close to this one, except multiplied by -1. And if you think about it, this is sort of an element of the rotation matrix. So you can rotate this one. You could use a rotation where this one's just flipped, like in a mirror. An admissible rotation matrix is to just, I mean, I think it's called improper because it messes up the chirality of the mirror, but it's still admissible. So you could just multiply this first loadings matrix by -1 and multiply the first factor that you estimated by -1 and just report those. And in that case, they look like they match pretty well. And the same, yeah, and I'm sorry, you also said this one's also multiplied by -1. But then I think it would look pretty good. Yeah, okay. We can compare the two covariances. So in this case, I'm just making a plot of, assembling the covariance matrix from each loadings matrix and plotting the value of the covariance matrix, the true one on the y-axis, the estimated one on the x-axis. And they fall close to a one-to-one line. So it's able to recover the covariances, I think, quite accurately. And that's important because people want to look at the sign of the off-diagonal elements. Basically they want to convert the covariance to a correlation and say, is species A and B, are they positively or negatively correlated? And if they're estimating the covariance precisely, that means they'll also get that sign correct, and the magnitude's correct. And then you can, show the, let's see, and these are the factors. So if you've got one factor, they're mirror images, you have to multiply by -1, and so that's why these are negative, on the negative one-to-one line. But yeah, it's recovering the omegas really well too. So it's getting the spatial pattern right, it's getting the loadings right, when you correctly specify the number of factors. So if you simulate dynamics with 3 factors and estimate it with 2, yeah, that's sort of this easy case to start with. This will take a while again. So it's, in this case, it's kind of a misspecified model where there's more covariance occurring than we're able to capture in the number of factors we're specifying. Maybe I'll start wrapping up. So I'll end when we look at these results. But does anybody want to ask any questions while this is running? Wrap up questions. On Thursday, the plan is to basically just look over this package FAST that I've built for vector autoregressive spatiotemporal model. So it's like a multivariate spatiotemporal model that builds in a lot of the features we've covered. So we can keep talking about factor models in that context if people want.
If you had in your model more factors than were actually truly existed, would you have 2 that worked and then 1 that was close to 0?
Yeah, exactly. Yeah, and you could use this script to confirm that. I don't think, just because I'm nervous about my car, I don't think I have to cover that. Makes sense. Yeah. And I also encourage you to show that in that case, AIC will, because they're all close to 0, AIC will show that those additional parameters don't improve the log likelihood much, but they're also counted against the model in in terms of the AIC calculation. And so in that case, AIC will do a good job of telling you how many factors you need to include. Where AIC falls over is when you've got this sort of like multi-causality, like if you're in a Whittaker world where you've actually got sort of just a tapering effects of these kind of declining importance factors. And in that case, it's kind of an arbitrary choice how many you put in. There's not, ecologically, it might be full rank, but you might not need full rank to predict well. And so you can kind of see that AIC will not really have any obvious logical choice.
Yeah.
Okay, so in this case, if we do, if we compare these factors, it's sort of hard to say if they match well or not. I mean, I guess this factor, first factor actually looks pretty similar between the two. Like, it's the negative of that one, approximately. And this one, second factor looks a bit like the second factor, the true second factor. So in this case, maybe we got kind of lucky that it didn't. But like, there are definitely some cases where like the first factor is estimated as the negative of the first factor true, except for some reason the third row of the first factor is much more, much higher value than it should be, and maybe because it's picking up on the third factor, like the first factor is some mix of the real first and third. And so if you want to really look at how they compare for non-matching number of factors, you should just do the eigen decomposition. Eigen of and then let's see. So I'll end with this. It's where so in this case, it's gonna eigenvectors. So that for the true, only the first, the first three eigenvalues are non-zero, and all the other ones are essentially zero. So we can just look at eigenvectors 1 through 3, and those are the eigenvectors that matter. And similarly, if we look at the eigenvalues of the estimate, only the first two are non-negative, and then or non-zero, and all the other ones are zero. So we can look at eigen. I'll just so I can look at the same time. Eigen hat vectors 1 through 2. So if we look at it in this visualization, the dominant eigenvector for the true and the dominant eigenvector for the estimated, I think, look pretty similar in terms of the big values. So like negative 0.48 in the third row and negative 0.56 are really similar. And the ninth element is a big one. So for the big values are pretty well correlated to the dominant factor. And the second one also, like the fourth element, the eighth element, are getting pretty close. So essentially when we take dynamics that's generated with three kind of important elements and we project it down into a two-dimensional subspace, we're losing this eigenvector. So we're missing some kind of component of the covariance between species. And so if we compare the the predicted covariances, it actually still doesn't look terrible, but there's kind of this like pattern where some stuff is above and below the line because those true covariances include this action of this third factor that we're dropping in our model. So anyway, here's the code. I encourage people to play with, do these experiments of like if you estimate fewer factors than the true number or you estimate more factors than the true number. If you're interested, outside class. Any last questions? Are we good?